I think it's really successful, and thank you for everyone, because it's also scientifically very interesting. So in this talk, maybe we will go a bit one step in the direction of understanding a possible relation between quantum groups and quantum reference frames. So I'm very happy that I'm speaking after Czaslaw and also after Vittorio Desposito, who gave a talk yesterday. And also in this talk, we will try to make a relation also between the concept of quantum observer that emerges in the context of quantum space-time, so from a quantum gravity perspective, and the concept of quantum observer that emerges in the context of quantum mechanics when we talk about quantum reference frames. So we heard already in the talk by Fedele Lizzi yesterday that a way to model quantum properties of space-time is through non-commutativity, because in this way you introduce some fundamental uncertainty in your capacity to resolve space-time events. In general, you can model non-commutativity in this way. I'm not going to go into details here. What is relevant for our talk is that when we introduce non-commutativity in space-time, then automatically we also introduce deformed symmetries, and we model them as quantum groups or Hopf algebras, as Fedele described yesterday. Then in the context of quantum mechanics, we are seeing that there is another emerging notion of quantum space-time in some sense. And this happens when you attach a reference frame to a quantum object. Okay, so this is the notion of quantum reference frame. And for what I'm going to say here, it is relevant to notice that, at least in simple cases of models of quantum reference frames, you can basically separate the phase space of the system that you are measuring, and this would be governed by a commutator with h bar, and then the phase space of the reference frame. So here I'm putting a different constant because I want to be able to make a classical limit only for the reference frame. So this is h bar, but I'm calling it kappa just so that I'm able to make the reference frame classical while keeping the object, the system that I am observing, quantum. So what I'm going to discuss is looking for a way to relate these two notions. And the tool is to look at the symmetries of these transformations. So on the one hand, the transformations that describe symmetries of quantum space-time, so quantum groups. On the other hand, the transformations that describe how you transform from one quantum reference frame to the other. And the discussion will be a two-step discussion based on this work jointly with Flaminia Giacomini and Ángel Ballesteros, and recently also with Diego Fernández Silvestre, who is a PhD student. So the first step is to identify the group structure that is defined by quantum reference frame transformations, and to show that this is some Lie algebra that is 7-dimensional that reduces to the usual Galilei algebra of quantum mechanics when you go to the classical reference frame limit. And then the second step is to establish a correspondence between this group structure here and the group structure of a quantum Galilei group. Now I will make a little spoiler, so if you have to get one take-home message from all the talk, it's the following. What we find is that these quantum reference frame transformations, in fact, correspond to a quantum Galilei group, but not the full quantum Galilei group, only if you consider the group at the first order in the quantization parameter of the group. And at the end of the talk, I will give some additional comments to try and suggest when is it that the full quantum group structure should emerge. The other important thing is that this correspondence is found once you identify the quantum deformation parameter of the group with some physical properties of the reference frame, of the quantum reference frame. And in particular, we will see that the quantum deformation parameter of the group basically is the inverse of the mass of your quantum reference frame. Okay, so to start, this is just one slide to establish notation. This is just standard Galilei group giving symmetries of a free particle in quantum mechanics. You have generators of boost, time translation, space translation. Then you have the central extension corresponding to the mass. The group element is just given by exponentiating the generators with some group parameters. So this is an object that will be very important later. And the fact that this is a group simply means that if I compose two elements of the group, I get another element of the group. And this happens if the group parameters satisfy some composition rule. For example, if you take the translation parameter A, you see the usual thing that you have to include also V times the time translation parameter when you compose two translations. This is maybe a non-trivial way to show it, to write it for some of you, but it's the usual thing that we know about the Galilei group. And when you want to act on some system, you can represent the generators on the physical variables of the system so that you can do computations. Now, the other ingredient that we need, as I said, is quantum reference frames. And here I will take a very simple scenario, which is the scenario that was proposed in 2019 by Flaminia, Esteban, and Czaslaw. So we have three particles. We take one particle as the object that we are observing, and the other two are the two reference frames from the perspective of which we can look at the other two. And as I said, I assign a different name to the non-commutativity parameter of the phase space of the reference frame so that I can make it classical when I want. So when you act with the quantum reference frame transformation, basically what you are doing, if you want to transform from the reference frame of a quantum particle to the reference frame of another quantum particle, what will happen is that the parameters of your transformation are not numbers any longer, but they are operators. And they are the operators corresponding to the phase space variables of your quantum reference frame. And as I said, it is possible to show that when you consider this kind of transformations, you can show that they close a group structure. Well, here is how they act on the phase space of the phase space variables of particle B. What is relevant is that if you want to close the algebra generated by these two operators, so this is the operator of quantum translation, and this is the operator of quantum Galilean boost, then you will find that you will need to add these other generators. And these elements all together, so you see there are 7 generators, they close an algebra. This is how it acts. And what is really interesting is that these additional operators that emerge when you ask that you have an algebra that is closed, so that you ask that there is a group structure, in fact, they are exactly the operators that would show up if you require that these transformations are extended symmetries of the Hamiltonian of free particles. So it all makes sense all together. Now we go to the quantum Galilei group. So this is one slide a bit on how mathematically you define a quantum group. So the main point is that you take the group element, the same kind of group element I wrote for the standard Galilei group, but then you promote the transformation parameters to operators, so to non-commutative operators. So you see that there is already a similarity with what we had in the quantum reference frame case. In general, the commutator of these parameters will be ruled by some non-commutativity parameter that is what I call the quantum deformation parameter. This is a parameter that is not h bar, it's another thing. It's what makes the group quantum. And we will see a specific example in a second. Now, if we take the quantum Galilei group, so we are working in 1+1 dimension. This has been studied, and there is a classification of all possible quantizations of the Galilei group. There are 26 of them. And then we look for one that is as close as possible to the structures that we have seen in the quantum reference frame transformations. So we ask that the time translation parameter is commutative, because we want a commutative time. And then we ask that the space translation and the boost parameter have a non-vanishing commutator, because eventually we want to recover the non-commutativity of phase space. And just these two requirements single out one quantum Galilei group of all the available ones. So let me show you how it looks like. For the moment, I will skip this bit and I will go here. So the commutator of the group parameters are these ones. Here alpha is this quantum deformation parameter. And here kappa, now let me go back here. So you start to build the quantum group. First, you define Poisson brackets on your transformation parameters. So you can think about them as dynamical parameters, but not quantum. And then you quantize the Poisson brackets. And the quantization parameter of the Poisson brackets, I will call it kappa. So the same object that I used already for the quantum reference frame, because eventually we can identify them. So here we see that we have two parameters. One is alpha. Alpha is the parameter that tells us that the group is a deformation of the Galilei group. And kappa is the parameter that tells us that the group parameters are quantum objects rather than dynamical objects. Okay. Now, this is a mathematical structure. We want to give it a physical interpretation. The physical interpretation comes once we represent the generators and the group parameters on some phase space. Okay. And I will represent the generators, so P0, P1, and kappa, on the phase space QB and PB, so the phase space of the quantum system that we are looking at. And then I represent the algebra of the parameters of the group on the phase space QA and PA, so the phase space of the reference frame. Okay, so the interpretation at this point is that the transformation generators act on the phase space of particle B, so on the quantum system we are looking at, and the group parameters act on the phase space of the reference frame. Okay. This is the representation. You don't need to look at the details too much. So, and this is the representation of the generators. Putting everything together, we build these objects. So these are very similar to the objects that I was looking at when looking at quantum reference frame transformations. So these are objects that act on the tensor product of particle A and particle B. And they take this form. And for comparison, that will come in a second. And when I exponentiate them, I obtain the operators acting on the phase space. Now, here comes the point where we put this structure in relation to the quantum reference frame. So first step, I already anticipated it. We identify these two phase spaces on which we represented the generators and the group parameters with the phase space of the quantum particle B and the quantum reference frame A. Additionally, as I anticipated already, we take the first order in the quantum deformation parameter alpha. So to the first order, we can write things in this way. And then final point, we take the ansatz where alpha, the quantum deformation parameters, is 1 over the mass of particle A times phi. Phi is, appears here in the representation of V. Given this, we can write the transformation generators. Oops. And now, finally, we can make a direct comparison between the quantum Galilei group objects, which are here. You see they act on the tensor product of the two phase spaces, and the quantum reference frame operators that we defined before, that again act on the tensor product of the phase space of particle A and particle B. And if you look at them long enough, you will realize that these operators here are just linear combinations of the operators of the quantum Galilei group. And this basically means that we are looking at the same symmetry structure. In fact, if you write the full group element by exponentiating, you will see that this is exactly the same object, because you can go from basically one basis to the other by recombining, by changing the order of the exponentials. And I want to say that this is a really non-trivial thing, because so we have seen that the quantum reference frame group is finite, is 7-dimensional. In principle, a quantum group, so a quantum Galilei group, is infinite dimensional. So it's really non-trivial that we end up also from the quantum group with an object that is finite dimensional and has the same dimension as the quantum reference frame group. How many minutes I have? Okay, very good. Thank you. Yeah. Okay, so this is, let me just go back. Okay, here. So let me emphasize again that we found the equivalence between these two structures once we looked at the quantum group to the first order in the deformation parameter, and we identified the quantum group, the quantum deformation parameter with 1 over basically the mass of the reference frame. So this is the main point. Then we want to understand a bit better why is it that we have to take this first order in the quantum deformation parameter to recover quantum reference frames. And here it becomes useful that I had a different constant for the quantization of the phase space of the reference frame. Okay, so let's take a semi-classical limit. So instead of having the quantum phase space for the reference frame, we go to a dynamical case, so we have Poisson brackets in the usual way. When we take this limit for the phase space of A, and we write again the quantum Galilei group operators, what we get is that these operators are a tensor product of something that, on the left, is a classical but dynamical object, where the dynamics is here. And on the right, we still have a quantum phase space, because it's the phase space of particle B. Now, we said that, so therefore, we said that the quantum Galilei group acts on a tensor product of Hilbert spaces for A and for B. So in general, we can write a generic state as the product of a state on A and the state of B. when we are taking this semi-classical limit, basically we are considering semi-classical states on the Hilbert space of A, such that the commutator is vanishing on those states. Now let's see what happens if we act with the quantum reference frame transformations on states of this kind. So we have a semi-classical state for A and the quantum state for B. Sorry. Okay, well, before going there, it's good to write this. So here we are writing the action of the quantum Galilei group on states, as I said, where the state in A is semi-classical and the state in B is fully quantum. Then you can write this exponential, putting on the left the classical but dynamical values for your phase space coordinates QA and PA. This is exactly the structure that I mentioned in the beginning when I was building the quantum Galilei group. So it's this semi-classical version of the quantum group that is called the Poissonly group. So what is relevant is just that on the left of the tensor product we have commutative but dynamical objects. Now let's add one ingredient. So instead of having one semi-classical state, we have a linear superposition of two semi-classical states for the particle A. And let's look, for example, at the action of the quantum Galilean boost on this kind of state. When you act on the first state, again, you can write the exponential with the classical group parameters here. When you act on the other one, again, you can have the classical group parameter here. But when you put everything together, this becomes the PA, so it becomes the quantum version. So what we are seeing is that this is exactly the quantum reference frame boost, the quantum reference frame transformation for a boost transformation. So basically what we are seeing is that we recover the quantum reference frame transformation when we act with the quantum Galilei group, not on a fully quantum state, but on a linear superposition of semi-classical states, okay? The conjecture, but this is hard, we don't have a proof, but the conjecture is that the full quantum Galilei group, so the quantum Galilei group at all orders in the quantum deformation arises when you take a fully quantum state for the reference frame, so not just a linear combination of semi-classical states. And okay, here comes my summary. So we have, we have seen that quantum reference frame transformations in this simple case of three particles where one of them plays the role of quantum system and the other two are the two reference frames from which we look at everything. These kind of transformations close a seven-dimensional Lie algebra. Then we have seen that this seven-dimensional Lie algebra is equivalent to the algebraic structure that you get when you build a quantum Galilei group and you consider its first-order quantization. And the crucial point in finding this identification is to identify the phase space on which the quantum group acts with the phase space of the quantum reference frame and the quantum particle. And as I said, you have to link the quantum deformation parameter alpha to the mass of the quantum reference frame. And yes, it would be really interesting at this point to understand better what happens if we take the full quantum group, which is the thing I mentioned in the end. So this is what, in a slightly different context, Vittorio was doing for the quantum group of rotations, SUQ2. So in that case, he was considering a fully quantum group, so you would expect to I mean, it would be very interesting to understand what is the relation with the state of a quantum reference frame, for example, in that case. And yeah, I think I'm done.
Okay, thank you very much. Okay, thanks a lot for the talk.
Sure.
We have again many questions, so let me.
We also have the discussion later.
Yes, we will still have the discussion, but we have some time for questions.
Good.
Thanks a lot for the very nice talk. I want to ask, how would the algebra change if you change the calculation from the quantum reference frame side instead of the semi-classical limit, instead of h bar go to 0 or set the m, but rather change everything to Poisson bracket?
So you want to change everything also at the level, also for, say, the B particle, for the quantum system? I'm not sure I understood.
So for the quantum reference frame part, if I change all the calculation from commutator to Poisson bracket, and from and how would this algebra change?
Okay, so if you have Poisson brackets for the reference frame, so this is the case that I was briefly mentioning basically here. So you take a dynamical limit of the reference frame. So it's classical but dynamical. Okay, in that case, what you recover at the level of the group structure is the Poisson-Galilei group, which is what I have here. Let me this object here. So the parameters of the group transformation have non-trivial Poisson brackets, but they are commutative because you are considering a semi-classical limit in that case.
Okay, we have a question from Czoslaw.
But we can discuss more because...
Thanks a lot for the talk. At some point you said that these new two elements, if I am not mistaken, dA and dB, that you needed to include to close the quantum group, that they are natural symmetries of the free Hamiltonian, if I heard this well. Can you say how really
I think you're
the Hamiltonian would look like? And the second question, is this just like you always consider just one system and one reference frame, or?
Yeah, so the case that we are considering is the very simple case in which you have 3 quantum particles and you transform from the reference frame given by C to the reference frame given by A. So it's a very, and it would be very interesting to generalize these to more complicated situations. Then we are considering that these are free particles, okay?
All 3?
Yes, all 3 of them. And this is the case where these operators are extended symmetries of this system. No, is this?
Okay, because it's recorded, you should use the microphone.
So from one reference frame you see just 2 of them, like I don't know, I'm C, then I see A.
Yeah,
and B.
yeah, exactly.
And then from the other you other C. So my question is, from the perspective, is this still a free particle, or you think about somebody looking at 3 particles from above, let's say, and these 3 particles are free Hamiltonian. You know what I'm asking?
Yes. You're asking who is seeing them as what?
Which case is the case when you say, oh, this is the symmetry of the free particles, dA and
well,
dB?
I think we can look at the Hamiltonian and see what is it. If I recall correctly, this is a free Hamiltonian when you write it from a relational Hamiltonian. So when you write it from the point of view of, say, particle C. But we can look at it to make sure that this is the case.
There's a question from Esteban.
Thank you very much for the talk. This is a question about the interpretation of this group generated by the transformation. So usually in QRFs, you have this exponential of X reference frame times P system, and this means more or less I am using my reference frame as a reference frame for position. And then you have e to the minus high P reference frame X system, and this means kind of I am using the frame as a reference frame for boosts, if you wish. And then you build an algebra out of those, like you put them together. So how should I understand this? Are you using the same particle as position and momentum reference frames?
Yes,
Or
so this is crucial, in fact. So xa and pi a, they are considered to be the phase space coordinates of a given particle. So this is really important, because then this is when so you are assuming these relations, and this is the phase space on which you are doing your representation.
Yeah. Because I could consider like jumping to B with X and coming back with P, and then I don't get the identity. So
Well, I mean, this is the point. So this is a group, so you know that there is a series of transformations that will bring you to the point where you started from. That is the, and the fact that you have to add these generators, where are they? The fact that you have to consider all these generators is, in the end, exactly what you are saying, is that this is the structure that gives you the full symmetry. So in your the way you said it, that allows you to go back from where you started.
Okay. So while we start to set up and change the microphone, there is time for maybe a very short last question.
Oops.
Thank you very much for the talk. Do you hear me?
Yes.
Yeah. You conjectured at the end that for if you have higher orders, or if you consider all the orders of the quantum Galilei group, you described a situation where the reference frame has a generic state. Did I understand correctly? Generic state. Yeah. Yeah. Could you interpret this as using a non-ideal reference frame in this situation? Could this be a different definition of a non-ideal reference frame? Because you are using a generic state for it.
I have to ask you to repeat, because I didn't get the beginning of your question, and
I just repeated your conjecture at the end.
Ah, okay, yes.
According to this,
I mean, I think we should agree on. You should tell me exactly what you mean with this non-ideal reference frame. But I mean, from my point of view, it is a reference frame that is in a completely quantum state. So, say you cannot write it as linear superposition of semi-classical, which I guess is what you are pointing to. Yeah, exactly. So in that sense, I would say yes.
Let us thank Giulia again for the nice talk.